One of the things calculus is really useful for in one dimension is giving us linear approximations to functions which are more complicated than linear functions. And we can do the same thing in higher dimensions. So for example, let's see how to estimate the change in the function f of xy equals x cos y minus y sine x when xy moves 0.1 units from the origin, in the direction of 1, 1. So I guess in this case, since the value of f of 0, 0 is 0, this means we're approximating the value of f 0.1 over root 2, 0.1 over root 2. Okay, so how we'll approach this is the tangent line at 0, 0 is a good approximation to f for small distances. So in that direction. So I mean tangent line in the direction of 1, 1. And in particular, the slope of that tangent line is equal to the directional derivative of f in that direction. Okay, so let's calculate the directional derivative. So let's see. So grad f will be, so we'll have cos y minus y cos x times I, and then plus, so it'll be negative x sine of y, and then minus sine x times j. Now the direction, I sort of already said this, but the direction of 1, 1 is 1 over root 2i plus 1 over root 2j. So I just normalized this guy in order to make this a unit vector. And so now if I calculate the directional derivative, in that direction, well, first I guess del gradient of f at 0, 0 will be, so this will give us, I guess, just I. Yes, because sine of 0 is 0. And so del f at 0, 0 dot 1 over root 2i plus 1 over root 2j is just 1 over root 2. And so now so this is the slope of the tangent line. And so we want to find the change in the function, we want to find the height as we go a certain distance along this. So the change will be approximately 0.1 over root 2, which more explicitly is about 0.0707. Okay, so in general, to estimate the change in a function f as the input, so x, y, but you could do this in higher dimensions, moves some small distance ds, so this is the small increment, in the direction u, starting from a point p0, we'll use the formula df is the directional derivative of f at p0, and then times that small increment. So be careful here. This needs to be a unit vector. So if you're just given something that's like in the direction of blah, then you need to divide by the length first, as we did in that example just now. And here by df, I guess we sort of mean the approximate change in f. All right. So now a closely related concept is the concept of the linearization of a function. So the linearization of f at a point p0, x0, y0 is the function, it's the linear function L of xy is f of x0, y0 plus fx at that point, x0, y0, and then x minus x0 plus fy at x0, y0, y minus y0. Now, it's been a while since we talked over particular about this distinction between points and vectors, but I just want to point out that in this formula you can think of like x and y are points, but then we move our coordinate system to be centered at x0, y0, and then x minus x0 and y minus x0. This is converting the points. This is sort of converting the points, or the point x, y, into a vector relative to to the center, and then applying the gradient of f. So so the linearization is the best linear approximation to the function at p0, and if we look in a particular direction, we can move this over. So the linearization minus the value, the linearization evaluated near the point x0, y0 minus the actual value there is this thing with the gradients. And then, if we wanted to take the derivative in a particular direction, we could extract that information using a unit vector. And in particular, the tangent plane so the tangent plane at p0, you can see, is the graph of the linear function L of the linearization at p0. Okay, so let's do an example and find the linearization of this function. So I guess we've already found that. So del f at 0, 0. Let me just rewrite the formula for del f in general. So this we found was cos y minus y cos x times I, and then minus x sine y minus plus sine x j. So the linearization of f at 0, 0 is L of xy equals, so f of 0, 0 is 0. So we don't really need to write that. And then let me write all of this out and then simplify it. So plus fx 0, 0 x minus 0 plus fy 0, 0 y minus 0. Well, fy at 0, 0, this will be 0. This will be 0, and fx at 0, 0 will be 1. So the linearization at 0, 0 is just L of xy is equal to x. To make things more interesting, let's find linearization somewhere else. So linearization at the point, let's say, pi over 2 is, so now it'll be L of xy equals f pi over 2 plus fx at this point, pi over 2 x minus pi over 2 plus fy pi over 2 y minus pi over 2. Now this we can evaluate. So f of pi over 2 will be, I guess, so cos will be 0, so negative pi over 2. Fx there will be, since we're putting cos into both of them, this will be 0. And fy will be, okay, sine, both of those are going to be 1. So that'll be, I guess this will be negative pi over 2 plus 1. Yes, that looks right. So linearization, maybe I'll clean up some of this. Okay, so the linearization at pi over 2 is L of xy equals negative pi over 2 minus pi over 2 plus 1 y minus pi over 2. And you could like expand that out and simplify it and whatever, but we could also just leave it like this. We'll finish off with one more small comment. So we said the difference, the difference between the linearization and the original value at the original point, this is fx, x0, y0, x minus x0 plus fy x0, y0, y minus y0. If we write dx to be the change in x, and dy to be a small change, change in y, then we'll also see this written as fx dx and fy dy. And so this expression is called the total differential of f at the point p0, x0, y0. There's a sort of fancier mathematical way of talking about what these like dx and dy really mean, but sort of in practice, you can just treat them as very small changes in the variable.